In part 2 of the Separable ODE videos, let's continue getting some more practice solving separable ODEs, and in particular, let's look at some initial value problems which contain separable ODEs. This is as good a time as any to introduce a way of writing differential equations, which is called the differential form of an ODE. Now we have this quantity dy dx, which represents the derivative of y with respect to x. And technically, this is not actually a fraction. This is the limit of a fraction, the difference quotient. But we have benefited occasionally from treating it like a fraction. For example, yesterday, we sort of got away with taking dy dx, quote-unquote multiplying it by dx, and quote-unquote canceling those dx's to reduce it to dy. So it is occasionally convenient to think of this quote-unquote fraction as having a numerator and a denominator. A numerator called dy and a denominator called dx. These quantities are called differentials. And we say that an ODE is written in differential form if it's written as some expression containing x's and y's multiplied by the differential dx plus some expression containing x's and y's multiplied by the differential dy equals 0. Now, this differential form, this ODE, would be equivalent to the following if we subtracted the m of xy dx to the right side and then quote-unquote divided by dx, then we could write this expression in a slightly more standard way. Function containing x's and y's multiplied by y prime is equal to negative m of xy. It would be more standard for us to write something like this with a y prime or a dy over dx than it would be for us to write things with dx and dy separately. But this is occasionally useful, for example, when we study exact differential equations a couple of sections from now. For example, here we have a differential equation which is currently in differential form. Let's go ahead and solve this differential equation. Now at this point there's only one tool in our toolbox, and when you only have a hammer, everything looks like a nail. So let's hope and pray that this equation is separable. I'm going to begin by rewriting this expression in a slightly more standard format. E to the x plus 1 cubed e to the minus x dy is equal to the negative of e to the y plus 1 squared e to the minus y dx. And I might as well just go ahead, divide both sides by dx so that I get that handy dandy y prime. Now currently our x's and y's are separated, but they're separated in almost the exact perfect wrong way. We need to get the y's on the left side and the x's on the right side. So let's go ahead and sort of flip everything around. Divide both sides by negative e to the y plus 1 squared e to the minus y. That's multiplied by y prime. And let's set that equal to what we have on the other side, which is 1 over e to the x plus 1 cubed e to the minus x. Now let's take just a minute and check and see if we divided by 0 at some point. So what do we have in our denominators? We have e to the minus x. An exponential can never produce a 0, so that's fine. We also have in the denominator an e to the x plus 1, but that can't be 0 because an exponential can't produce a negative number. And likewise on the left-hand side, those two exponential factors cannot be 0 for similar reasons. So there are no sort of separate special solutions that we may be missing by dividing both sides of the equation, and it's safe for us to proceed to integrate both sides of this equation. Now, in anticipation of the integration that I'm about to have to do, I'm going to do a little bit of rewriting of these expressions. Instead of having an e to the minus y in the denominator, I'm just going to flip that to the numerator and change the exponent to positive y. Same thing over here on the right side with e to the x. Now this looks like a good opportunity for a substitution. For example, on the left-hand side, if I set u equal to e to the y plus 1, then du would be equal to that e to the y dy that I have in the numerator. So I would be effectively integrating negative u to the minus 2 du, moving it out of the denominator. On the right-hand side, I'm going to do something very similar. I'm already using u for something else, so maybe I'll use v. I'll use v equals e to the x plus 1, so that dv is equal to e to the x dx. And that transforms the integral on the right side into v to the minus 3 dv. So integrating both sides, u to the minus 1, the right side is going to give me negative 1 over 2 v to the minus 2 plus c. And if I return these to being in terms of x and y, then the u to the minus 1 will be equal to e to the y plus 1 to the minus 1, and the right hand side will be equal to e to the x plus 1 to the minus 2 plus c. Okay, the integration is now complete, so we now begin the task of algebraically solving for y. The first thing really that I need to do is get rid of this exponent of minus 1 on the left side. So one way to accomplish that, for example, would be to just reciprocate both sides. E to the y plus 1 is equal to 1 divided by what I will write as negative 0.5 e to the x plus 1 to the minus 2 plus c. Then I can subtract 1 from both sides, and I get e to the y equals this fraction minus 1, and therefore what would y be equal to? Y would be equal to the natural log of this expression on the right. Now there may be a way to simplify this that's not obvious to me right now, but I can't really think of a good reason to simplify this any further. So I'm just going to leave it at that. The functions of this format are the solutions to the given separable ODE. Now let's go ahead and practice solving initial value problems containing separable ODEs. For example, let's solve the initial value problem where we have dy dx plus 3y is equal to 1, and we require that the solution that we give in the end satisfies that if you plug in x equals 0, y equals 7 is the result. So in the initial value problem, I'm going to begin by finding all the solutions to the ODE. So y prime is equal to 1 minus 3y, so that I have nothing that's being added to or subtracted from y prime. And then I'm just going to divide by everything. 1 divided by 1 minus 3y, y prime is equal to 1. Now let's consider what we just divided by. We just divided by the quantity 1 minus 3y. And let's figure out what the consequences would be if it equaled 0. If it equaled 0, I would get 1/3 is equal to y. But among other things, this function does not satisfy the initial condition. This function constantly outputs 1/3, so it could never output a value like 7. Therefore, we can disregard this possibility because it would not actually be a solution to the intermediate value problem. So let's go ahead and proceed to integrate both sides. on the left side, I will get, by chain rule, negative 1/3 natural log of the absolute value of 1 minus 3y. And on the right hand side, I will get x plus c. So let's go ahead and clean this up a bit. This would be the natural log of 1 minus 3y is equal to negative 3x, negative 3c, but there's no real need to have negative 3 times c, so we can just refresh this into a brand new added unknown constant. Now we can use the exponential to get rid of the logarithm, which means that 1 minus 3y is equal to plus minus e to the negative 3x plus c. But via the standard trick, we can go ahead and roll this into 1 minus 3y equals some number k e to the negative 3x. Continuing to work on isolating y, let's do a little bit of rearranging. Negative 3y is equal to k e to the negative 3x minus 1. And so now let's divide everything by negative 3. We get y equals k divided by negative 3 e to the negative 3x plus 1/3. But k divided by negative 3 is still just an arbitrary unknown constant, so we can refresh this if we want and turn this just into a new k. So this would be the general format of the solutions to the ODE. Now let's make sure that the initial condition is satisfied. Let's try and figure out the value of k, which would cause y of 0 to equal 7. So I'll plug in 7 for the y value and 0 for the x value. I get k e to the 0 plus 1/3. So k would be equal to 7 minus 1/3, which would be 20 over 3. And therefore, the particular solution that solves this initial value problem is 20 over 3 e to the minus 3x plus 1/3. One more example, a little bit more robust. Let's solve the initial value problem. Dy over dx equals y squared minus 1 divided by x squared minus 1. And we require that if we plug in 2, that 2 should also be the result. Okay, so let's rearrange this. Let's bring that function of y over to the left-hand side, multiplied by dy dx, and leave the x's on the right-hand side. Now, let's figure out what we just divided by. We just divided by y squared minus 1. So let's consider the consequences of having a y that was equal to plus or minus 1. Now, if y is equal to either the constant function plus 1 or the constant function minus 1, it's never capable of outputting 2. So in this case as well, those two constant functions do not satisfy the initial condition, so they can be discarded. So let's work on integrating 1 over y squared minus 1 with respect to y, and 1 over x squared minus 1 with respect to x. This is another prime opportunity for partial fraction decomposition. If you have 1 over something minus 1, I'll just use u as a stand-in for the x on the right and the y on the left. Then this could be split up as a sum of a fraction with u minus 1 in the denominator and u plus 1 in the denominator. So again, using the Heaviside cover-up method, we can fill in these blanks. The first fraction corresponds to a denominator which zeroes out at positive 1. So if I plug positive 1 into the left side, covering up u minus 1, I get 1 over 2. And similarly, for the second fraction, I get negative 1 over 2. So as a result of that decomposition, I now know that the left side is 1/2 y minus 1 plus negative 1/2 y plus 1, and similarly for the x's on the right side. So let's go ahead and integrate this. We have 1/2 natural log of the absolute value of y minus 1 minus 1/2 natural log y plus 1 equals 1/2 natural log x minus 1 minus 1/2 natural log of x plus 1 plus c. Alright, that's a lot of halves, and that's a lot of natural logs. What I'm going to go through and do is just multiply everything by 2. Including the plus c, but technically that doesn't really matter because c times 2 is just a new arbitrary coefficient. Now once that's done, the 2's and the halves will destroy each other, and I will be left with natural logs that I can combine. For example, on the left side, I have the natural log of y minus 1 divided by y plus 1. And that's the same thing as the natural log of x minus 1 divided by x plus 1, plus our newly refreshed c. So now, to get rid of that natural log, let's go ahead and exponentiate both sides. So I get the absolute value of y minus 1 over y plus 1 is equal to e to the entire right side. Now in order to get the e and the natural log to be able to cancel each other out, I'm going to need to move this plus c out of the way. So I'll do that using the normal trick of turning it into a k constant multiple. So I get y minus 1 over y plus 1 is equal to k times the absolute value of x minus 1 over x plus 1. Now, again, the absolute value really only has the effect of adding a plus minus sign to the equation, but that plus minus can be rolled into k. So this becomes y minus 1 over y plus 1 equals k times x minus 1 over x plus 1. Now here's a little trick that may serve you well. When you're working on an initial value problem, it's not always convenient to wait until the very end of the problem to find the value of the constant in your solution. What I'm going to do is I'm going to take a moment right now, before I solve for y, and try and figure out what the k would be. Solving this for y seems like a huge mess, so I'm just going to try this and see what happens. So I plug in 2 for x and I plug in 2 for y, and I get 2 minus 1 over 2 plus 1 on both sides, which means that k is equal to 1, which means that the solution that I'm looking for in this intermediate value problem satisfies the property that y minus 1 over y plus 1 equals x minus 1 over x plus 1. Now you can go through the rigmarole of clearing all the fractions, painstakingly sorting out the terms that contain y from the terms that don't contain y, factoring and dividing. But I'll give you a bit of a spoiler. Look at these two expressions. They're exactly the same except for x is on one side and y is on the other side. These two expressions would be absolutely identical in the case that x is equal to y. And therefore, the function y equals x makes this equation true. And therefore, the function y equals x is the solution. If you have any doubt, just go all the way back to the original differential equation. All the way up here. If I set y equals x in this differential equation, then dy dx is just going to be equal to 1. And if I set y equals x on the right-hand side of the equation, I get x squared minus 1 over x squared minus 1, which is also equal to 1. If I have the function y equals x, and I plug in x equals 2, then the result is that y would also have to be 2. Therefore, y equals x satisfies all the conditions of the differential equation, and so y equals x is our solution. The moral of that story is, every once in a while it's convenient when you're working with an intermediate value problem to find the value of your constant before you finish isolating y. Every once in a while you do get lucky, and it makes the problem a little bit easier. That concludes today's material. We practiced solving more separable ODEs. We had a look at the differential form of an ODE, and then we practiced solving initial value problems which contained separable ODEs.